Yeah.
In the week section?
In which week we are?
Oh, let's see.
It should be week 9.
I think so.
Last one.
Let's see here. Let me just make sure.
20. Yeah.
Yeah, right? Yeah. I just did. Usually I bump them to the top, but I don't know. I guess I just left it at the bottom. But. Oh.
Sure.
Well, it's because I counted reading break as week 7. It's not really a week typically, so I might change it. But.
No, it's like a
Week.
guide.
Yeah, it's like, okay, here's, yeah, exactly, right? Oh, and I do want to show you guys, so what I did over the weekend, and because I know I made you guys work really hard on lab 3, and so of course, I think you'll find that I was pretty generous when I was marking. I read through them all and I was pretty happy with what I saw. So, but what I did was I just made my own, right? And so you can have a look. So I posted my RMD as well as the HTML, and just so you can have a look and see kind of what I would have done. I'm not saying that that's how everyone should do it. It's just one of the ways that you could have approached each of these problems, right? And so I'm not even saying that it's the most clever way, or but what I tried to do was tried to do the simplest way for each of them. And there's fancy, complicated ways that you could do it, right? But I don't know, for some reason, RMD files, you'll have to copy and paste them into a blank one. I think you can handle it, right? But right, so here I said that this is only one way to tackle these questions, right? Lots of different ways that I saw that work and are still good. And so maybe have a look at that. And then here's my output that I got. And so just one of the ways, just so you have some sort of guide. I also, this weekend was like, for you guys, marked your labs. It's tough because you're my 4th course, and so I've got all this like normal amount of marking and stuff to do, and then I'm like, okay, gotta do you guys. I posted all the rest of your assignments. You'll notice that they're just like 5 multiple choice questions, right? And so it should be pretty good. You could probably get 100% on all of them already because you can just try your way. But it might be good to use them for just practice. And then of course the extra practice problems that aren't for marks, but just if you want to practice, see some more questions, right? That aren't necessarily using R and that kind of stuff, right? So what I decided to do for this week was, because here we are in week 9. Like I said, I used reading week as 1 week. So anyways, we're just going to continue working on lab 4, right? Because we're going to wrap up chapter 5 today. And so then you'll have seen everything from chapter 5. And then we'll just keep working on lab 4. So there's no new lab, it's just lab 4. And I'm pretty sure, I can't remember when I made it due. Friday, did I bump it to something later? Monday, Friday? Does Friday work for you guys? Do you want it Monday? Monday? Sold.
Then there will be 2 assignments for this week and the next week.
Say that again.
So if you give this assignment to the Monday, so there will be 2 assignments for this week as well as for the week.
Oh no, because there's no new lab this week. It's just lab 4. So I'll shift the due date as well as post it on Moodle. I'm surprised. I must have deleted it, that it was the due date, or maybe I didn't post it on there. But so we will continue working on lab number 4 this week. Oops. And we'll shift the due date to Monday. How about Monday at midnight? Why not? Now do Monday, is that March 9th? At 11:59. Hey, no problem. And then there's no new lab this week, right? We'll just keep working on lab 4. In fact, you could probably get a good chunk of it done, but I know you guys have other stuff, so I'll let you handle your own planning, okay? So, so there's no new lab this week. We'll call this chapter 5 continued. And I wasn't really using section headers, but just for reference, because it will be kind of clean from now on, we're gonna do 5.6. I know, confusing. I made it kind of mumble jumble because it was kind of jumping back and forth a lot in the previous sections, and then now, because I like to give you section headers, I'm trying to give you section headers. So 5.6, and you guys are gonna love this section because it gives you rules for what transformation you might want to do. What? It's not just eyeballing and fun times. So it's called using plots to help choose a scale, for the response. Okay. So far we've said, okay, well, if I'm in an Anova situation, right, I've got a numerical response and one categorical predictor or explanatory variable, right? Then I'm in an Anova situation. And so what we do is we're gonna make box plots, right? Side-by-side box plots, just to see what this data looks like, right? And so if the response is numerical and the explanatory variable is categorical, right? This is what I call an Anova situation, right? That's what we're assuming that we've got for this part of the course. So if we have an Anova situation, we plot the relationship using side-by-side box plots. or dot plots if you prefer, but for me, box plots, I prefer them. Okay. What are we looking for? We said that we're looking for symmetry, right, in our distributions for each of the categories, but also equal variability, right? And so what we're looking for, symmetric distributions for each category, but also few, hopefully no outliers, right? But we're also looking for, we can handle a few outliers. Oops. But not a huge amount. Well, that's going to be go with your gut type of situation, right? It depends on how desperate you are to analyze it, right? And so for the outliers, right, we can handle a few. So we would argue, okay, there's a few outliers here. I'm recognizing that, but I'm still going to go ahead and do my analyses. So yeah, can handle a few. Manuel's favorite thing, a few. So yeah, but we're also looking for approximately equal variability around in each of the categories, right? And so roughly equal variability in each of the categories. So just like a transformation, right, works if we have some sort of curvature in our data, we can transform it to make it linear, right? We can do transformations or re-expressions on our response variable to address mainly that third point. So here, we can often transform or re-express the response variable if the variability in the categories is different, right? Or if because I've got the arrow, how about if this condition is not met? If this condition is not met. Okay. One way that we can check it, okay. So one way we can check the condition of equal variance, we can check the condition morning. So one way we can check the condition of equal variance, right, which is basically what this roughly equal variability in each categories is. Everyone's back from the weekend. Hey. Is to compare the group with the smallest standard deviation to the group with the largest standard deviation. So we can compare the standard deviations of the groups, is to compare the standard deviation standard deviations, I guess, in the groups. Specifically, we want to compare, so we would calculate the maximum SI. So this is the largest standard deviation. For some group, divided by the smallest standard deviation largest standard deviation, right? So now if you've got a group with a huge standard deviation, right, as long as it's the biggest one, you would take that maximum standard deviation of that group, group 1, for example, and then over the smallest standard deviation of group 3 or whatever, right? And so what you would need then is you would need to calculate the standard deviations for each group. Right? And then you take the maximum over the minimum, and as long as less than 2, as long as that ratio is less than 2, then the condition is met. If it's close to 2, you might want to look into it, right? Because that means that the maximum SI is almost 2 times larger than your minimum, right? And so that's, you know, kind of a big deal. But in general, if it's larger than 2, if that ratio is larger than 2, then we need to look into it, right? And so if max SI over the min SI is larger than 2, we cannot assume roughly equal variance and must consider a re-expression or a transformation of the response. It's hard to transform categories, right? So we have to focus on the response. Now that everyone's on the line, I'm going to pause it here. I'm going to take you to Moodle because I do want to show you before I forget that I posted, so this weekend I posted what I would have done for lab 3 because it was a big lab, right? And there's lots of ways that you can do it. Like I said, I'm not saying that that's the best way, the only way, or even the most clever way. I just tried to find the simplest way to do all of these things, right? And so sometimes it's elegant, sometimes it's not. It's just one way that you could have answered all these problems, right? So I posted the RMD and the HTML so that you can have a look at how I tackled those. Right? And also for a guide of kind of what things should start to look like. Okay. So we've got this little check-in point, right, of the maximum standard deviation over the minimum. If it's kind of less than 2, then we're good. If it's larger than 2, then we have to consider some sort of re-expression. And so most often, if we need to transform an Anova, right, an Anova type of response, then we use a log transformation, right, a natural log. But there's some other methods that we could use. And so most often in Anova, if we need to transform the response, we typically use a log transform. A natural log ln, but we just write log. Log is ln. For all of stats, and basically, unless you're dealing with sound waves and stuff, then log would be base 10, but otherwise in the rest of the world, typically we're dealing with log base E. You guys are kind of on the edge though, because computer science uses log base 2, right? So, but in stats, whenever you're doing statsy things, if it says log, it means the natural log. Okay. So, what can we do to figure out if a log transform is going to be appropriate? Well, you could try a bunch of stuff, but this is what I was saying, that you guys are going to love this. Kind of a rule book for what our transformation should be. What? Have you ever felt so lucky? So, what we have to do is, the first thing we have to do, we can follow these steps to determine, and there's going to be a lot of steps here, right? But we can follow these steps to determine the best transformation. Okay, step number 1. You have to find the means and the standard deviations of each of the groups. Find the means, which we'll denote by yi bar, and standard deviations, which we'll denote by si, of each of the groups. Of each of the groups. Okay. Tricky, because if you have, say, 4 groups, right, you're only going to have 4 means and 4 standard deviations, but that's okay. Step 2 is going to be to take the log of each of the means and each of the standard deviations. Okay, so then generate the logs of each of these. So then calculate the log of the yi bars and the log of the si's. Okay. Because typically our go-to transformation is going to be the log. We use that as kind of a, I don't know, a starting point. Step 3, what you're going to do is you're going to make a scatter plot of the log of the standard deviations against the log of the means. Okay. So make a scatter plot And this is why don't be jolted if you only have 4 categories, for example. You're only going to have 4 dots on your scatter plot, right? So it might look a little bit weird, but that doesn't matter. So make a scatter plot of the logs of the SIs versus the logs of the YI bars. So logs of the SIs against the logs of the YI bars. Let's say you've got group 1, group 2, group 3, group 4. 1, 2, 3, 4. Right. 4 groups. Yeah. Then what you do, now we've got a simple linear regression here. So what we're going to do is we're going to fit a straight line. And even if it's not linear, right, in this case we could probably, but with 4 data points, we shouldn't really say anything about linearity or anything like that. So what we do is we fit a line of best fit. Might go something like this. So step 4 is fit the linear regression line and find the estimate for the slope. And find the estimate for the slope. You can eyeball it too, right? You don't have to actually fit the line and find the estimate, right? We could eyeball it too. Right, we could eyeball it. For us, because I know you guys like rules, you can fit the linear regression line, find the slope, and then what we use the slope for is to figure out what our transformation might be, right? And so we use the slope to determine what transformation to use. There's a table and everything. What transformation to use. The transformation that you're going to use is y to the power of 1 minus the slope. Okay. So here, this is the transformation. Should have given myself more room for the transformation, right? But the transformation is going to be y to the power of 1 minus the slope. So if we've got a slope of 0, 0.5, 1, or -1, so what we do is we just kind of go for whichever one's closest, right? Kind of approximating. Right? Then we've got our transformation. If the slope is 0, right, nothing going on here, then you've got y to the power of 1. So then you've just got no transformation and you just use y. So then if you've got a slope of 0.5, then you've got a transformation of y to the power of 1 minus 0.5, which is 0.5 square root of y, right? So then you can use a square root transformation. If the slope is 1, then you use the log of y. And you can use calculus to show it. You'll have to take the limit, but in my mind, to convince myself, I just say, well, if the slope is 1 here, then the log that I've used to make that line makes sense, and I'm just going to keep using it, right? So yeah, just that one is like, but then, so if you find a slope of 1 or roughly 1, then you use a log transformation. And if you have a slope of -1, then you actually just do 1 over y, which also is not very obvious to me, right? So those last two are less obvious. When you use the y as y to the power of 1 minus the slope. Right. But anyways, so these are approximations. So approximate guidelines. But it's just nice to have. Typically, I mean, you're going to find they have a slope of 1, and you would only go down this road if you look at your box plots and you think that you need to kind of shrink down the variability of some of these guys, right? And so if you look at your plots and you have roughly equal variance in each of these categories, then you don't need to do this, right? Then you don't need to re-express the y, right? It's just if you're looking and you say, hey, there's actually very little variance in this group, and then huge variance here, and then smaller variance here, huge variance here, then you might need to look at kind of transforming these things and shrinking them up. Yeah.
What happens if you have values greater than 1 or greater than smaller than?
I don't know. Use a log. I think because we're taking the log, it might put a kind of a limit on what they might be reasonably. But honestly, I'm not sure. I haven't played around with it too much. So.
Or is it logical if, let's say, if it's a positive number,
Mm-hmm.
we stay with the log, and if it's negative number, we stay with the 1 over 1?
Yeah, I think that sounds reasonable, right? These should handle all your situations, right? You could get fancy and do, you know, a third root or something like that, but I wouldn't do a third root if a square root sufficed type of deal, right? So, and again, you could try all your re-expressions to see which one kind of, and then so how you would go back and measure it is you could compare again the maximum SI over the minimum SI to look at that ratio right after you've transformed your data, right? So then you could do a comparison again, and if it's decreased, right, it shouldn't increase because then you did it wrong, right? Then you've increased the variability in your groups. But as long as you've gotten to less than 2, then you can keep going. So there's one little pickle, because in the second part here, we calculated the log of the yi bars, usually the SIs, but remember we can't take the log of 0, right? Just as a math rule, right? We can't take the log of 0. And so, or a negative number, but that's okay. And so we can't take the log of a negative number nor 0, right? And so usually the pickle is if our response has 0 values in it, right? So if our response has values of 0 in it, what we do is we just add a small amount, right? And it depends on the scale that you're talking about, right? If your responses are from 0 to 100, then adding 1 unit won't really make a difference, right? The difference between 0 and 1 won't make a difference. But if you're talking about, you know, from 0 to 2 are your responses, then adding 1 unit is too much, right? So then you would maybe add 0.01 or something, right, to get it off of 0, but just off of 0. And so if our response has values of 0 in it, we add a small amount and I'll put in brackets here, relative to the spread of our responses, right? Relative to the spread of our responses before we take the log, right? It should still behave like a very small number. And so how much you add, you know, depends on the situation, what you're talking about. But that's the trick that you're going to use, right? Because sometimes if you're trying to take the log of 0, it's going to complain and say, hey, I can't do that. So then you bump up your responses by some, and you should bump up all your responses, right, by that amount. I'll add it here. Yeah. Add a small amount to all of the responses. So
It's the same thing like when you do a regression and you get a model. There is an initial car price. So you have the intercept, right?
yeah.
So if you want to make the model to start at 0, you subtract that values from every other observation.
Yeah, you could do that. But in regression, we don't really need to do that, right? But one way that you could think about it is if you wanted to just look at the treatment effects. So then you take away the grand mean, right, that initial mean of everyone, and then you just look at, and you boil down and look at the treatment effects, right? So, and I think that's kind of on the same road as what you're talking about, right? But for us, right, in order to figure out what transformation or re-expression we should use, right, before we can do any of this, we need to take the log of the responses. You would do the same thing for the standard deviations, but a standard deviation of 0 is not very interesting. And so that's not something that we would look at, because then all the points are on the exact same value. No variation, nothing to talk about, right? There just seem to be happening there. So a standard deviation of 0 is not going to happen, right? So that's why we focus on the responses, the logs of the y-axis bars. Okay, so pretty cool, pretty fun. Rules. All right. Any question? Let me just make sure I didn't forget to. No, I talked about the +1. I talked about the max SI. I will say that after the response has been transformed, right? So after the response has been transformed, we can calculate the max SI of the transformed one over the min SI, right? And make sure that it's less than 2. We can calculate the ratio. It'd be nice if it had a name, but I didn't see a name for it. I think they just max SI over min SI. The ratio should be smaller, right, than before the transformation. Should be smaller than before the transformation. Otherwise, we did something wrong. Right? Otherwise, we increase the difference in the variability. So that's how we would tackle if we're faced with an Anova. So we've got those box plots that we're looking at, and we've got kind of unequal spread in each of these. Then we could do the transformation. A transformation sometimes will also deal a little bit with the symmetry, right? It'll kind of even things out a little bit, but we do the transformation to tackle the difference in variability, right? If we have unequal variability. Okay. Any questions? Not yet. I know. You guys are good. You'll stop. All right. 5.7 is the last section in chapter 5. 5.8 is just a case study. But what I'm going to do is, and I had to do other stuff this weekend, other courses. I couldn't spend my whole weekend on you guys. But what I'll do is I'll put together kind of a general Anova analysis document, which is essentially what you can use to do lab 4, right? You can use that as a guide. What I'll do is I'll use that case study in 5.8. It's the words with friends example. But what I'll do, because the example that they do, they say, oh, everything looks fine, so we're not going to investigate anything like that. What I'll do is I'll actually go through and show you how you would investigate things. So there's going to be a lot of extra stuff in there, right? To keep an eye out for, but I want you to have a document before you do lab 4, because it's kind of like a, here, go analyze this stuff. Fine, I felt okay doing that kind of stuff with regression, but because Anova is pretty new, regression, I mean, we're more comfortable with typically, but because Anova is new, I'll ease into that. So 5.7 is on multiple comparisons. And Fissures least significant difference. Least significant difference, which we'll abbreviate LSD. What? Or a drug. Yeah. 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 I'm sure it has a new name, but yeah. Anyways, not really our realm. But so one thing that we've decided, right, is, okay, we run an Anova, and Anova tells us if something's going on in there. So then we said, okay, well, once we figure out that something's going on in there, then we can go and we can look at our data and see which groups might be different from the others, right, and that kind of thing. But wait, right, what happens every time that you do a pairwise comparison, for example, is, so you could break it down and you could just do 2 sample t-tests all around, right, for all the different combinations. One thing that you have to keep in mind, though, when you're doing multiple comparisons, because that's what you're doing then, is you're kind of breaking down and looking at these pairwise comparisons, is every time that you run a t-test, right, there's an alpha probability that you make a type 1 error, right? If you use an alpha of 0.05, then there's a 0.05 probability of making a type 1 error. That's in one go, right? Every time that you run this pairwise comparison, you expose yourself to a type 1 error again, right? A type 1 error is when you reject H0 when you shouldn't have, right? And so every time that we try something, hey, is this significant? Hey, is this significant? Hey, is this significant? We expose ourselves to more and more type 1 error, right? Or the potential of more and more type 1 error. And so there's lots of ways that we can deal with that. For example, later we talk about just, okay, if I'm making 5 comparisons, for example, I'm going to split my 0.05, my alpha 0.05 into 5, right? And so now the alpha level that I'm going to use is 0.01, right, for each of these tests. That's one way that we could do it, but we'll parking lot that for now. Because here, the other way that we could do it, or there's lots of ways, of course, but we could talk about Fissures least significant difference, the LSD. And so now that helps us just compute a difference, right, at least significant difference. And so any difference that's larger than this amount would be considered significant, which means we're not actually running any tests, right? We're just saying, okay, a difference larger than this, significant, right? I know it's hard for me to convince myself that I'm actually not using any alphas, right? Because in my mind, I'm still doing a hypothesis test, but because I'm not relying on the t-distribution anymore, right? Or I am once, right? And that's why we're able to get around it. Okay? And so when we make multiple comparisons, we expose ourselves to type 1 errors. We expose ourselves to type 1 errors with each comparison. With each comparison. And for me, I have a hard time, or I did, I guess, wrapping my head around type 1, type 2 errors, right? What's bad, what's good? Well, neither, an error is bad, right? But type 1 errors are typically worse than type 2 errors. And so that's why we talk about type 1 errors more. And so how I had to memorize it was just memorizing this table, right? Where we've got some truth where, okay, H0 is true or H naught is false, and then on this side, I've got my conclusion, right? My conclusion from my data, and I'm gonna scoot this over just a bit here. My first option is that I reject H naught. Or I fail to reject H naught. Right, all of this is in terms of H naught. So my conclusion, if I reject H naught, if the truth is that H naught is true, well, that's an error, and that's a type 1 error. And that happens with a probability of alpha. If I reject H naught and H naught is false, well, that's not an error. In fact, that's what we call our power. And it's not important, but it's 1 minus beta. Right, we haven't talked about power yet, so, and I'm not sure that we might touch on it. Who knows? Yeah. If I fail to reject H naught and H naught is true, right, then that's all good. Then we have a probability of 1 minus alpha of that happening, and there's no problem here. In fact, there was no problem with our power either. Our power is just the probability of rejecting H naught when it should be rejected. And if we fail to reject H naught, but H naught should be rejected, right? H naught is false, then we've got a type 2 error, which happens with a probability of beta, which we don't really pay attention to betas or type 2s too much. I'll move type 1 up here. There. Right. So here's an error. Actually, write it in red. And type 2 error. So how I finally had to buckle down and get a handle on these things is just memorizing this table and just kind of going from there, right? Because from this, whatever the situation is that you're talking about, right, you should be able to tell yourself, okay, well, if I reject H naught, but H naught is true, right, then I've made a type 1 error, whatever that means, right? I've told you that you have a disease when you actually don't, right? Typically, type 1 errors can be thought of as kind of false alarms, right? And so we can often, and there are situations where it doesn't quite work, but we can often think of type 1 errors as false alarms. Right? If you take the disease example, right? If I'm a patient, I wouldn't be very happy if they told me that I have a disease that I don't have, right? But that's better because then I can go and have further testing done and then confirm that I actually don't have it. Oh, what a relief, right? I'm not very happy or alive, right? If they tell me, oh, nope, you're free and clear, right? No coronavirus here, right? And then it turns out that I do, and then you know? And so here, if I reject H naught, that's the same as saying you have the disease, right? Whether that's true or rejecting H naught is, in this case, oh, I always get these backwards.
So your H naught is you have
Your
a virus,
H naught is that you
have virus, which is equals to, and your HA is you don't have virus, which is not equal. Is what
But usually we use no change for our H naught, and that's where my hang up is. So if I'm saying, okay, if H naught is that I do not have the disease, yeah. H naught, I do not have the disease. I reject that. I have a disease, is the conclusion. But I don't have the disease. Okay, let me write that down. So if H naught is patient does not have the disease, only because your null hypothesis should always be the one of no change, right? Nothing going on here, right? So H naught is always a statement of no change. Phew, okay. Think we've got it under control. So that means if I've rejected H naught, I'm saying, hey, you have coronavirus, when in fact they don't, right? False alarm. You do further testing, right? If you tell someone that they have a disease, if it's, you know, serious, then you would probably run another test to make sure, right? And whereas if you send them home and you say, nope, nothing to see here, right? But you're wrong, they have the disease, right? Well, that's a type 2 error. I don't know if there's a fancy, it's kind of like it's a false negative, right? You get a false positive and a false negative. So a type 1 is a false positive, and a type 2 is a false negative, if you want to think about them that way. Although type 2 errors are a concern, right? There's something to look out for, right? There's a reason that we hinge everything on the alpha, right? We've talked about alpha, we've heard about alpha before. You might not even have heard about beta before, well, in regression, but this is a different beta, right? So type 1 errors are usually the ones that we're more concerned with, right? And so I think I already said it. Anyways, I'll say it again. We are usually more concerned, and I'm using vague language for a reason, right? Because there are always going to be situations where the opposite is true, right? But more often than not, right, we're usually more concerned with controlling our type 1 error rate. With controlling our type 1 error rate. Which is our alpha. So Fissures Lsd is one way that we can control our type 1 error rate. Fissures Lsd, least significant difference, is one way we can control the type 1 error rate in multiple comparisons, right? As soon as we're doing multiple comparisons, the type 1 error rate in multiple comparisons because every time that you run this test, right, you expose yourself to potential false positives, right? So you're finding a difference, or you're finding a significant result when there actually isn't one, right? And that would be bad. And like I said, we'll come back to this and we'll look at other ways to control it, but the one we're going to start with is the Fissures Lsd. Okay, so what is our LSD? LSD is just going to be a number, right? So it's going to be a distance that we compare to the difference between the means that we want to compare. So Fissures Lsd will give us a value, will give us a value and a difference between two means that's larger than this one, right? Our least significant difference. Least significant difference is 2. For example, if we find a difference of 3, then that's larger than our LSD, and so we have a significant difference. So Fissures Lsd will give us a value which we compare to the difference between two means y1 minus y2, for example, bar. If the LSD is less than y1 bar minus y2 bar, meaning the difference is greater than the least significant difference, put that in kind of notes here. The difference is greater than the least significant difference, only because I find it's more helpful if you phrase it that way. So greater than the least significant difference. So if the least significant difference is less than the actual difference that you're observing, we can conclude the difference between y1 bar and y2 bar is significant. So how do we calculate this LSD? The LSD is going to be a T star times the square root of the mean squared error times the square root of 1 over n1 plus 1 over n2. We could also write this as T star times the standard error because the standard error is the root mean squared times the square root of 1 over n1 plus 1 over n2. I wrote that down yesterday, and then I was like, I should check that in the textbook just to make sure that I'm not lying. Isn't that nice? It's true. Okay, to get our T star, right, let's break this down a little bit. Our T star with degrees of freedom equal to the error degrees of freedom. And a confidence level that you've decided, right? Usually 0.05, alpha of 0.05 corresponds to a 95% confidence level, right? And some confidence level, usually 95%, right? Unless you want to adjust it. The root of the mean squared error, we've seen that a ton of times before, right? This is just from our Anova table, right? And so this is from Anova table, right? The mean squared error. N1 and N2 will be group specific, right? So if you're comparing N1 and N2, then you use their sample sizes. What's nice is if you have the same sample size in each group, then of course our LSD is going to be the same for all of these, right? But it could change between the groups that you're comparing. Right, so here, this depends on the groups being compared. Another thing that I thought of was this looks a lot. It is nice. Look at me go. T star times the square root of the mean squared error times the square root of 1 over n1 plus 1 over n2. That looks a lot like our margin of error for our confidence interval, right? And so, and it is, right? For the difference between two means. And so essentially what we're saying, and this I kind of just came to me, I was like, it's the margin of error. I knew it, but I was driving, so that's why I had to check now. It's the margin of error. So if the difference that you're seeing is larger than the margin of error, then you can say that you have a significant difference, right? Essentially, right? Because here, and we're not going to do that, right? But here, this is your margin of error. What we're saying is for the difference between two means, right? And so what we're saying is the difference, actually, sure, let's do it. Otherwise, it's like, what are you talking about, Emily? Recall that the confidence interval for y1 bar minus y2 bar was y1 bar minus y2 bar, right? The difference between the two means, plus minus t star, which we found the exact same way, right, with the error degrees of freedom and whatever confidence level we want, times the square root of the mean squared error times the square root of 1 over n1 plus 1 over n2. So then what we're saying here, right, this is our margin of error. Which is our LSD, if you want to call it that. So therefore, if y1 minus y1 bar minus y2 bar is larger than its margin of error, we have a significant difference. Is the connection that we can make. But usually we don't call it the margin of error, we just call it the LSD, right? The least significant difference, because that's the method that we're using. Give credit where credit's due. Yeah.
It's a two sample test. That's what we're doing.
That's right. Yeah.
I remember we used to have two conditions for that.
For two samples, we're checking normality, right? Independence is usually a go-to assumption. Is that what you're thinking? Right, we're assuming that all our observations are independent of each other. But that kind of, we just assume that always, even when it's not true. Well, there's ways that we can deal with it, but for us here, we just assume that we have independent observations. Usually we say IID, identical and independently distributed. So everything's IID. So you might see that if you're reading on Wikipedia or whatever. Okay. Any questions about that? No? All right. I was gonna do a recap, but I think what I'll do is I'll just put it into that document, right? For the general methods, I'll just put it all in that because I won't have time to do it in 2 minutes, and so I'll post that document. Hopefully I'll do it today or something. Post it for you guys. But remember, lab 4 is the one that we're just gonna keep working on that one, which was the analyze this Anova style data set, right? Very vague, very open-ended. Just do everything that we can. And so the one that I'll post will be kind of a guideline for you to follow. Any questions? No? All right. Oh, and like I said, I posted the assignments. I didn't put a ton of thought into picking questions.